So, today we're going to talk about forced motion, which basically means that we have exactly what we had in 5.2 and in 5.1, but now we have some external force that might be driving what is going on. So imagine we have a mass on a spring, and maybe the spring is compressed and then released, but now we have some other force that drives this back and forth. Why not? Well, you'll see that this has a lot of applications to things that are very important to us nowadays, but
it's like when you play with the slinky and you're like,
that'd be one application, but I was thinking more like, flying, things like that.
Slinky is more important.
Okay, so here's the model. We're going to go right to what we had before, which is MA equals minus KX. And if there's damping, then we have that same proportional to the velocity force. And the only part that will be new is F of t. Okay? So this is our external driving force. Now, if we move some stuff around, then what we'll probably do is write it as mx double prime plus kx. Actually, no. Usually we wrote mx double prime plus beta dx dt plus kx. And instead of it equaling 0, now we'll have it equal f of t. Okay? So this will be a great place to start, and obviously you can divide by the mass and do all the other stuff that we've been doing. So sometimes we'll look at it as x double prime plus 2 lambda x prime, just like in the last section, plus omega squared x equals capital F of t. So this new function is now little f divided by the mass. So sometimes we'll look at this equation, but again, this is where you want to start. So for all the application problems where they give you a weight and you got to find the mass, you got to find the spring constant, it's just easier to start right here, plug everything in, and then solve the equation. Okay? So let's do an example. And I think at this point you know how to find masses and spring constants and all that. So let's just start with, let's assume we've plugged in everything. So the mass is 1/5. And maybe it's 1.2 times the instantaneous velocity for the damping force. Let's say the spring constant is 2. And I'm really not sure why I switch the notation, but that's okay. And let's say that the driving force is equal to 5 cosine 4t. And some conditions. Initially, we are a half unit below equilibrium, right? And let's say, yes.
Since for the second equation that you wrote under the box one,
Uh-huh.
you divided everything by n.
Uh-huh.
Shouldn't. Oh wait, you changed the f to be capital.
Yes.
So
Yeah.
That's like f small.
Small f over m.
Okay.
Yeah. Okay. So to solve this equation, we're going to go through this together because I know it's been a few days, but first we should probably do what? So x double prime plus 6x prime plus 10x equals 25 cosine 4t. And now, how do we solve an equation like this one?
Annihilator.
Sure, you could do the annihilator method. So first we got to find the complementary, the auxiliary equation will get us there. And that'll be m squared plus 6m plus 10 equals 0.
Wait, why are you using empty with these?
So just start off with you can use that one.
It's the same thing.
Okay, but it's just better this way.
That's how we do it.
Okay, I'll listen to my students. All right, so we're going to use the differential notation instead of the auxiliary. Either way, we're going to find the roots of d squared plus 6d plus 10, which is the same quadratic as we had earlier. So quadratic formula will tell us that the roots are -6 plus or minus 36 minus 40, right?
Would it be -3? Oh.
That must.
No, we just divided by 2.
Oh, your step. Yeah, I'm getting there. Slow down. So this will be -3 plus or minus I. Is that what you were saying? Yeah. I was still working it out. Okay. So what is the complementary solution going to be? Yes. Times. Good. You guys did learn stuff last unit. See? Okay, so there's the complementary solution. Once we have the complementary solution, then we're going to want to annihilate the right side. So now we would have to use what to annihilate the 25 cosine 4t. That is correct. So let me.
Wait, what about 6? Oh.
Wait, is that supposed to be a 10?
Yeah, it is. So original is in black. I am annihilating in pink. So that now I get this, right? So from here, we get our entire solution. Our general solution will be exactly what we had before. And we have some new roots from the d squared plus 16. Those are
C3 cosine 4t.
good. So the stuff that's in pink, this is your complementary, right? This is your particular. So x sub p of t, let's just call it a cosine 4t, so I don't have to keep writing c3 and c4, plus b sine 4t. We have to find the coefficients, so you know the drill. Why don't you guys take a minute and find the constants?
What does a P stand for again?
Particular.
Okay. Got it.
I will slowly write my solution up here. You guys work ahead of me now. here are my constants.
I had this.
If you did not get those, check. Well, first of all, check your derivatives. Second, probably make sure that you got to this point right here. You should have 25 cosine 4t's. There are 0 signs, so that's how you get those two equations.
Oh, no, I did have those two equations. Get that.
You just messed up the algebra. Or, yeah. What did you have?
10/9 for B and negative 5/18 for
Hmm. And you had these two to start. Anybody else getting these?
A.
Okay.
A is negative 25 over 102, but I got B is
What did you get for B?
negative 4 over 20.
Huh.
Oh,
Well, okay, so we agree on A. I just used the second equation, plugged in A, and then divided by 6 so that this became negative 4. So then that's 100 basically over 102. So I'm not sure. I think this is good. And you got it too, right? Okay. Anyway, let me make sure the video is still going. All right. So let's write down what we have. Right now we have x of t equals e to the negative 3t times c1 cosine t plus c2 sine t. Hello. Minus 25 over 102 cosine 4t plus 50 over 51 sine 4t. Okay, so we've done a lot of the harder stuff. We still have to go back though and find what? Yes. And now we do have the conditions from before. I'll rewrite them. X of 0 was a half, right? Yes. And x prime was 0. Okay, so we're going to have to find the derivative. So that'll be fun. Skip to the end. But are you going to skip to the answer on the exam?
No, this is the last.
It is. But it is important. Plus e to the minus 3t, and then minus c1 sine plus c2 cosine, and these are easy. Plus 100 over 50, or 100 over 102, which is 50 over 51 sine 4t, plus 200 over 51 cosine 4t. Okay. So if x of 0 is 1/2, so go back to the beginning. What does that tell us? What terms will cancel out when I plug in 0?
Well, the sign.
The signs cancel out, so all we have left is going to be c1 minus cosine of, that's just 1, so minus 25 over 102. So c1 will be something. Thank you. And c2, well, let's see. We know x prime of 0 is 0. And again, so now we look at x prime. The sign terms drop out. So we're going to have negative 3 times C1 plus C2.
It's off the screen.
Oh, let me. Where was I? C2, that cancels, so then plus 200 over 51. Thank you. So C2 is negative 86 over 51. Okay. So let's write down again what we have, and now we are done with the solution, but there are some details that are very important that we need to discuss. Okay, so we have final answer, our position equation. X of t is e to the negative 3t, 38 over 51 cosine t minus 86 over 51 sine t. And now the particular was
Negative 25 over 102 cosine of 14
thank you.
plus 50 over 51 sine of 14.
Okay. So again, I want to focus on, this is the complementary part of the solution, right? And then this last part here, that's the particular part of the solution. Okay, so here's a question for you guys. What's the limit as x approaches infinity of the complementary solution?
Wait,
It's negative 3. So
you mean it is supposed to be as t approaching?
Yes, that is supposed to be a t. See, even I still make that mistake. T is the independent, not x. So as t approaches infinity, that's going to be 0, right? Everyone agree with that? Okay. For this reason, we call x sub c the complementary solution. This is called the transient term of the solution, because over time, this term basically disappears. Okay? The other part of the solution, the x sub p, that's what we call the steady state solution. Because over time, if the transient term disappears, we agree that that's not going anywhere, right? That's because of the driving force, so that's still going to be in action as long as we have the driving force still driving it. Okay? So I do want to have these graphed. So just so you guys see what's going to happen, the first one is the final answer. Y2 is my transient term, and then Y3 I think was my driving or the steady state solution. So if you look at the graph, so this is our final answer. Wow, that's pretty slow. Wow, look at it go. Okay, and then here is the, what was that?
The steady state.
That was a transient, and this is the steady state. So as you guys can see, the transient term had a little bit of a contribution to the overall solution, but then pretty quickly after that, it pretty much was near 0 anyway. Does that make sense?
What was near
The transient term.
as time goes on.
Zoom
The
in.
transient was just turn off the other solutions.
Yeah.
Sure, I can turn off the other ones. So turn off main. Oop, nope.
Oh,
Oh boy,
the ball.
I'm really messing that up.
Just the ball.
Turn off the main solution. Turn off the steady state. This is the transient solution. Oh, you can't see it. There are some dots. It starts like right up here. and basically looks like around 1.5-ish. It's pretty close to 0 at that point. Okay. All right. So
Yeah, it's pretty
it is pretty pathetic. So our driving force is what's really. I mean, you guys see the difference that the steady state solution and the final solution are pretty much one and the same
Yeah,
after a certain amount of time.
graph.
Oh, that's what, oh, I didn't know.
Okay. So there is something I do want to mention though, all right? Because we'll talk about this in a minute. So let me go back and let me turn these other ones off. I said off. There we go. Let's just make this normal. And so I don't know if you can tell, but certainly as we start tracing because of the transient solution, which contributes to it a little bit at the beginning, there is kind of a spike in amplitude where it's a little bigger in amplitude at the beginning than it is near the end, if that makes sense. Okay? That's what engineers are really interested in. Okay, so let me actually write this down. Actually, let's write down a few things. Number one, the particular solution is pretty much the movement of the mass over an extended period of time. Our graph generally is going to look something like this.
Yeah, just really
Thank you. Where maybe there's some sort of peak in amplitude based off of these values here. So this green one is our transient term. That's x sub c. Okay. But now, what this leads us to is something that we call resonance. So we're going to talk about this real quick.
Really exaggerated.
The definition for resonance is essentially when a system oscillates with larger amplitudes at certain frequencies.
Wait, do x sub p and x sub c, do they meet the x-axis at the same time or not necessarily?
Not necessarily.
Heard this word used when speakers.
Okay. So look, essentially, I can tell you why this is important, and then we'll kind of look at the math behind it to determine when this might happen for certain scenarios. And I think even the book has these stories in there, but long time ago, okay, I believe it was in the 1950s or 60s. I can't remember exactly which decade it was. But there was a big plane crash where the wings of a plane pretty much just snapped off and everyone plummeted and nothing good came out of that. Okay? What had happened was that basically, and if you've ever flown on a plane, you know that the wings flutter a little bit. They have a little bit of give. They have to. Okay? But what happened was that the oscillations of the wings with the oscillations of the engines, the wobble from the engine, were too much, and that was what we mean by resonance. The amplitude of the wings' vibrations peaked, and they were too much to handle, and they snapped off. Okay? And this is something that back then the engineers didn't foresee happening. Obviously now we know more, but that's stuff that, this is important things to be on the lookout for. So if you guys are engineers and you're designing some planes, please, save us from our impending death. Okay. So let's look at what needs to happen in order for our system to be in resonance, when that spike is going to occur. All right, so let's start with our model. After I've divided by mass, and we're going to set this equal to some force that also vibrates. So let's say sine gamma t. All right, we're going to bypass a lot of the manipulation. I'm just going to say, here's what the solution is because we know how to solve it, and talk about the conditions that arise. So the solution for this is going to look something like this. A times e to the minus lambda t times sine of the square root of omega squared minus lambda squared t plus phase angle. So this, we already know this. This is just the way that we can write our answer in one trig function. So it's the same formula from before. So this is not a surprise. Okay, this is exactly the solution we got back here. Do you guys see that all we're doing is changing the complementary into this format? Okay, we're just keeping all the variables there. And now for the steady state solution, that's going to end up looking like f0 over the square root of omega squared minus gamma squared plus 4 lambda squared gamma squared times, and I'm trying to try to squeeze this in here, sine gamma t plus theta. Okay, sorry about that. But basically they're the same format, okay? They're both periodic. They both have their own kind of amplitudes. That's what the A is from the first part. And then the second part, that's the goofy amplitude thing that we would get. What's that?
What's on the new?
Yeah, it's this times, sorry, all of that. That just made it look worse. I am sorry. Just put it in the numerator. Yeah, it's okay. And again, here's what we know.
Wait,
From-
so this is the second part is the particular?
Yes, so this would be the complementary, and this is what the particular is going to look like. Again, we're not going to spend 15 minutes getting all that, but that's what it's going to be. Yes?
Also, is this going to be like something we should put a box around?
No, actually, we're going to get to that. I'll let you know when we get there. So we're going to go through a lot of the manipulation, or bypass that, and get to the important stuff. So here were the assumptions. These are from before. The amplitude for the complementary was the square root of c1 squared plus c2 squared. Sine of phi was c1 over the amplitude. Cosine was c2 over the amplitude. Okay. Over
plus theta or phi?
theta. This is a phi for the phase angle of the complementary. We're using theta for the phase angle of the particular solution.
Okay.
So two different angles.
Gonna be different.
Yes.
Nice. Cool.
All right. So now what we're going to do, we're going to just call this G of gamma to make things a little easier in a little bit. Okay, see ya. And then the bottom part here are some of the assumptions for the second half, sorry. The sine of theta are going to be minus 2 gamma lambda over the square root of, well, it's basically this denominator here. And let me just squeeze that on here.
Why?
These are the assumptions for when we write,
Always simplify.
when we combine our cosine and sine equations into one nice sine graph, right? These are the conditions that we have for the phase angle. Ultimately, that's not really going to be what's important, but it's worth mentioning. Okay.
What are we getting? They're just telling us.
So basically, as I was saying earlier, we're interested in the particular solution, which is this beastly coefficient, which I'm calling G of gamma for now, times sine of gamma t plus theta. Okay, now this is bounded for the amplitude. That's just a sine graph, right? So we know that that amplitude is going to be whatever the amplitude is. But because this function out here is so goofy, there could be some sort of peak or some sort of spike. So we want to know when that maximum oscillation is going to occur. Okay? So in other words, this part won't really do much to find the maximum oscillation. The only thing that's really going to help us find that maximum oscillation is this weird amplitude coefficient in front of the sine graph. Okay? So that means to find max oscillation, we need to find the derivative of that, which isn't so bad.
Well,
Is it product?
Yeah, so I'm just gonna do,
No, you're
so if I take the derivative of, I'm just gonna do product rule there, or quotient rule, whatever you want to call it. We're gonna do f naught times the derivative of the denominator, so that'll be omega squared minus lambda squared squared minus 4 lambda squared omega squared, or gamma squared, sorry. And that is now to the negative 3/2.
that whole thing's.
Yes, this whole thing is.
And
And
what,
So that W minus beta squared is still on its own.
Yeah.
this,
Gamma, gamma.
that's still squared, yeah. Yes.
why is your amplitude bounded?
Because this amplitude is fixed, like it's bounded, it's always between -1 and 1, right? For a sine graph.
Yeah,
We're interested
The
in
amplitude
when
is
the
going to
spike-
change depending on what this function is in front of it. We're interested in when that amplitude is at its highest.
so is that just the same like type of formula that we're looking at? It's like A sine.
Yes, it is. It's just goofier because we
So
have
then
this.
you could treat G of gamma as A.
It is its own A, yeah.
But it's a very.
It's a very complicated A because of all the different parameters involved. Okay.
You said G. Where's it put a negative 3 is?
So I'm doing basically the. Actually, I don't even need to do the quotient rule. Basically, I have this constant f naught, and I'm taking the derivative of the square root, right? So since that's technically to the negative 1/2, we decrease the exponent by
Isn't
1
it just like whatever the derivative of the denominator is? Is it that denominator by itself still?
to the negative 1/2, right? Because it's in the denominator. So that needs to go to the negative 3/2, and I'm still not done. I still got to do the chain rule, right?
Yeah.
So what's going to be the derivative of what's inside of the square root there? With respect to, remember, respect to gamma. So we have to take the derivative of this portion, so that'll be,
2 parentheses,
yep,
omega squared minus gamma squared times negative 2 gamma
yes.
minus 8 lambda squared gamma. Yeah.
I messed up somewhere. Oh, right here. That should be positive. I wrote that down wrong from before. So that should be plus. You were right, though, Jacob. Okay.
Minus should be a plus.
Which one?
The
This one.
outside of the parentheses that he just changed.
I didn't see.
All I did was rewrote what was in the square root, but I changed that to a minus on accident. Okay. And then when he said negative, I realized red flag, that shouldn't be negative. So what did I do wrong? So I went back and figured it out. Okay. So here's the point. This, because the point of finding the derivative is to set it equal to 0, right? So we can find out when that maximum is going to be. This coefficient, this whole thing out here, is never going to be 0. Ever, right? So the only place that we're going to get 0 is going to be from this second part. So if I take a look at that, that's 2 omega squared minus 2 gamma squared times negative 2 gamma plus 8 lambda squared gamma equals 0. So that's the part we're going to set equal to 0. I'm just going to simplify. That's minus 4 omega squared gamma plus 4 gamma cubed plus 8 lambda squared gamma equals 0. All of these I can take out a negative 4 gamma, which leaves me with omega squared minus lambda or gamma squared minus 2 lambda squared. Again, we're looking for gamma, right? This is a function in terms of gamma. We want to know what gamma needs to be in order to figure out when this max is going to occur. So this is not going to equal 0 because then that's not going to help us any. But this part is what we're interested in, okay? If this were equal to 0, then we wouldn't have any of this giant mess to begin with. You guys understand that, right? Even, I mean, technically that does give us a 0, but we wouldn't have that because that wouldn't produce the scenario we have. So this is what we need to have. So then if we get this part equal to 0 and move over the gamma squared, that means that that gamma has to be the square root of omega squared minus 2 lambda squared. Okay? So this is the condition. And this is really ultimately what again? Where was the very first time we saw this?
F naught sine of gamma t.
So it's really the coefficient of the driving force in the trig in the sine part, right? So all this mess ties back to this coefficient. If this coefficient is equal to the square root of omega squared minus 2 lambda squared, which is back from, I don't even have that page anymore. Okay. You guys have it though. That's when the system is in resonance. So when the period of the external force,
Off the screen, you can't see.
and I am totally over time, but sorry.
I was just gonna not say.
I'm sure you guys don't care. The wheeling's like, ah.
I care deep.
Yeah, uh-huh.
You care about sleep.
When the period of the external force is 2 pi divided by that lambda coefficient, that's what the period would be, right? Or that gamma coefficient, sorry. The system is in resonance. Okay, in other words, if we tie this back to the definition, which says that we have maximum oscillations at different frequencies, as long as we know the period, you guys know how to find the frequency, right?
Yeah.
Frequency is just what? Yeah, it's the reciprocal of that, okay? So if the frequency is square root of omega squared minus 2 lambda squared over 2 pi, that's when the system is in resonance. Okay?
So to be in resonance means that there's going to be some spike
In the amplitude. Exactly.